Welcome to the first Nordic Webcast. We'll be interfacing with Nordic SoftDevices. And why are we doing a webcast? We want to focus webcasts on giving more understanding to you out there on how we have done things and how our solutions. And we have made it not for people that don't know anything, but we assume that you know something about microcontrollers in general and that you have worked with them before. We have chosen SoftDevice to be our first topic because it's kind of the main difference between what you use on a normal microcontroller and our microcontrollers. You need to use this protocol stack or SoftDevice to be able to use BLE. So my name is Petter Myhre, and with me today I have Hung Bui.
Hello Petter. Hello everyone.
So I worked with Hung for 2 years, and we are in Oslo, and we are responsible for part of the Nordic Developer Zone. This webcast will have 2 parts. We'll have the first part will be we present some topics to you, and during this presentation you can put in your questions, and then afterwards we will have a Q&A session where we'll try to answer the questions that is related to this presentation. Then I give the word to you, Hung.
Thank you, Peter. Okay, let's start. We will start with the question, what is a SoftDevice? As you may already know, we provide our SoftDevice as a pre-compiled hex file that you can download from our website, and you will have to use that hex file and program it separately from the application. And this will have bringing no link time dependency. That means you only have to compile your application and you don't have to recompile the SoftDevice every time you compile your application. And inside that SoftDevice, we have the radio protocol stacks. It could be AND protocol, BLE protocol, or the combination protocol. And we call them with the code name S110, S120, and S130, and so on. You can find the definition of each SoftDevice with the specification of each of them. And by having that, we can keep the stack and application separate, and you don't have to worry about the SoftDevice or the radio stack. You just focus on your application and how to interface with the SoftDevice.
So you have this blue part here, which is the actual SoftDevice. And this is an example of the S110 Bluetooth Low Energy software stack. And it implements all these different layers in the stack, but you don't really need to care about the stack. You just use the SoftDevice API and communicate with the stack. So what is important is that this is something we have developed, and it is fixed, so you can't change it. You can just use the API. And on top you have the application. You see that it's separate from the SoftDevice.
And that SoftDevice is located in a reserved memory space, and that ensures runtime protection. Your application would not be able to cause a bug inside the SoftDevice or a crash inside the SoftDevice.
Yeah.
And then we provide the SoftDevice API as a supervisor call. We will go deep into this in the next slide. And this architecture provides 100% event driven. So you interface with the SoftDevice via API call and event.
So you get an event, and then you react to this event if you want to, if there is something you want to do.
Okay, so where is the SoftDevice located? For the flash or the program memory is located from the top, the region 0 here, from address 0 to address called code R1 base, and you can find the value of this because it depends on which SoftDevice it is. The size of SoftDevice varied, so you can find this number in the SoftDevice specification. And for the RAM, it start from address 2000 2 millions, like this, hexa 2 millions, and until RAM R1 base. So the application region, RAM region, will have to start from RAM R1 base until the top of the RAM address. Same with the flash or the program memory. Your application have to start from region 1, and you have to make sure that you configure it properly inside the region 1. And here we have an example of S130 application that is to start from address 1C000, which is size 24,000 hexa, and the RAM start from this address with this size. This is for 32 kilobyte RAM variant. And I can show you a common mistake that we usually have. For example, here I have an example with S130 correctly configured, but if I click on, say, changing the device, I don't have 51422, but I have 51822. You can see that the address will be reset, and you have to type the correct address in, which is 1C000 again. So remember, don't forget to check if your memory configuration is correct.
But you also need to change the size, right?
Yes. Match the size with the size of your chip. You could have 128 kilobyte flash, or you can have 256 kilobyte flash, and so on. So make sure you configure it correctly.
So if you have 256 kilobytes, you will have 40,000 hexa.
Yes.
So if you add these together, you will actually get 40,000.
Yeah. And so SoftDevice not only reserve RAM, but also restrict access to some peripheral interface like the radio or the timers. I will show you in the next slide. And those restricted peripheral must be accessed via the API provided by the SoftDevice. It will start with SD underscore something. And you will have a hard fault error if the application access those protected registers via CMSIS directly. So here is an example that we have the peripherals that is on the chip, and when the SoftDevice disable, all the blue block is accessible from the application, but when the SoftDevice enable, some of the peripheral will be restricted or blocked, and you can find the complete list of the blocked resource by looking at the SoftDevice specification. In this case, I'm showing the S110 SoftDevice specification, and if you go to chapter 11, and you can find the information on block and restricted peripheral. For the block peripheral, you cannot access it from the application when the SoftDevice is enabled. And for those restricted, you can access it, but you have to use the SoftDevice API instead of directly access the register.
So the ones that are open, you can just freely use.
Yeah, and for the open, you are freely to use. Let's talk about the API provided by the SoftDevice. We have a list of API that it could be the interface for the application, and those protocol APIs will give the application the access to the RF protocol function. And those NRF API will give the access for the system on chip for the other peripheral, the restricted resource used by SoftDevice. So you have two types of API. One is protocol APIs, and the other one is NRF API, the system on chip API. And those APIs implement at a supervisor calls. So when you call an API, it will trigger an exception with or an interrupt with one particular service call number, and that will be handled by the service call handler in the stack to forward that call to the function inside the stack. And those API calls are non-blocking, so you will receive the return code right after the function or the APIs has been registered or validated inside the SoftDevice. And we have an example here. Here is those protocol API like SoftDevice enable or start advertising. And those here is the NRF API. Here is to access the flash, and here is to control the PPI.
So if you have this advertising start function, and because it's non-blocking, you call it, and then you get an error code back, and but that doesn't mean that advertising has actually started. It will start, but
I mean, if you receive an NF success, that means the command is queue and the
advertising will start.
Yes. Okay. And here is a diagram that's showing more detail on how it works. Those APIs using SVC call. So we have here an example of advertising start API call. And if you start it in your application with a call, this API have, for example, X. The number for this is X, and then that will trigger the exception to the SVC handle inside the SoftDevice vector table, and that will forward to trigger the handle SVC handle here, and then inside the SVC handle we will check the SVC number, and here in this case we have X, and this one will forward this call to the function inside SoftDevice, and then after it has done with the queue, and you will receive a return code telling you that if this command is success or have some error that you can check with this error code here. And then after that you can the application can continue with the next instructions. And what about events? For example, if you already start advertising and then you have a timeout, say after 3 minutes you have a timeout for advertising. That will trigger first is interrupt inside the SoftDevice of the timer is run out, and then that one will go into the advertising timeout switch here in the stack event handle. That one will push the event of the timeout for advertising into the event queue, and then trigger software interrupt 2 to send that to the application vector table, and inside that we will trigger the software. We will jump into the interrupt handle, which is software interrupt 2 handle. Inside that handle we have to fetch the event out using this SDBLE event get, and then we can call our BLE event handle inside the application. So inside the application you are free to catch this event and continues decide on what to do after the advertising timeout. This is how our SoftDevice can send an event to the application. Okay, and this part, Peter, will you help me on this?
So SoftDevice at runtime. So the SoftDevice processing is interrupt driven, and access to the CPU must be shared between the application and the SoftDevice interrupts. We have the Cortex M0 has 4 interrupt priorities and the main context. SoftDevice uses 2 priorities to implement its behavior. You have lower stack and upper stack. The lower stack is the highest priority, which is used for radio events or protocol events, and or the BLE link layer. And you have the upper stack, which is the SVC calls with the API and the BLE host. The application has access to two priorities and a main context. So you have application I, which you can use for critical interrupts where you need low latency. For example, a sensor or something like that. But from this interrupt priority, you can't call lower interrupt priorities. And because the upper stack is lower than the application high priority, you can't really call this. So you have to go down to application low or from main to call this.
I just want to add that on Cortex M0 we actually have 3 more interrupt priority, but those are for the system to send out hash fault or non-maskable interrupt and to reset. So it's not accessible from the application.
So here we have an example of nested interrupt handling. So if you're going to do an API call to the SoftDevice, you should either be in main context or in app-low context, as you can see here and here. If you try to do an API call from the app-high context, you will actually get a hard fault because the API calls has a lower priority. And here you see an example of if you do an API call and then you get interrupted by the high app interrupt, and then you can, and here you can actually be interrupted by the protocol interrupt, which would be a radio event where the lower stack needs the radio. Then you will continue in the app high, then you will jump down to upper stack. Here you have a radio event, and for example a connection event, and this will jump down to upper stack, and here you get an application event up to the application through the software interrupt 2. Now we're going to walk through a short example where we show you how to set up the SoftDevice, enable it, initialize it, and we will make a call to the API to start advertising. We'll change the device name and then try to understand the error return system. So here we have a simple example that we have prepared. This is different from the examples you find in the SDK. We have made this so that it's closer to the SoftDevice, so it's easier to understand what is actually happening. This is usually handled by the SoftDevice handler library in the SDK, but we have set this up this way instead. So first you have a buffer, and this is the buffer you use to get the BLE events from the SoftDevice. We'll talk more about that later. And the first thing we do is to enable the SoftDevice. And it has 2 arguments. We have the low frequency clock source and the SoftDevice assertion handler. So it's important that this low frequency clock source is set correctly. So here we have on our development kits we have an external crystal. So we have set it to extol. And you can see all the different options for low frequency clock sources here. So if you don't have an external crystal, you should use the RC oscillator. And if you don't set it correctly, the SoftDevice just wouldn't work because it can't check if the crystal is actually there or not. And then we need to enable the software interrupt 2, and we don't need to set a priority for this because it's already set in the SoftDevice. It's app-low priority, and then we continue over to enabling the BLE part of the SoftDevice, SDBLE enable. And here you have some parameters that you are setting, like the service change characteristic. But we won't go into detail on this today. And in addition, we need to define the software interrupt handler, because this is what the SoftDevices call when it has an event. So we have a loop here, and then we use the SDBLE event get function to fetch the event from the SoftDevice. And if it is a valid event, it will call BLE event dispatch, which we have in our application, and then we can react to that event. And this will be called in a loop until there are no more events pending from the SoftDevice. When all this is set up, we can do, for example, start to advertise. We have a function here that does that. Here we set all the different parameters for the advertising packet. We have a device name and UID and stuff like that. And here you, for example, set the device name that you want to use. And you can see that we always use this error code when we when we are communicating with the SoftDevice, because this is our way of checking that we are doing things correctly. So this will return 0 if the call is successful, which is NRF success. If not, it will return something else, and you need to check the error code. We will show you that afterwards, how that works. And then we just we set the advertising data, and then we call SD BLE gap advertising start, and then this will return and the advertising will start. So then we can show how to do this. Then we first need to flash the SoftDevice. Then we open NRF Go Studio, and then we select our development board. And we do an erase all. So now it's completely empty. And then we need to find the correct SoftDevice. For this example, we're using the S130. And so we select that SoftDevice and we program it. Now you can see we have two regions. We have region 0, which is protected, and region 1, which is reserved for the application. Then we need to compile this. Then we need to select the board we are going to program on. Go to Utilities, Settings, Debug. Here all the different boards we have connected will show up. Okay. And now we can load it into the chip. So here we have a master control panel, and now we can start discovery to see if there's any devices that are advertising here. You can see we have a lot since we work in a wireless company. But here you have our device, Nordic Webcast. Here you can see all different information about advertising data, the complete local name, Nordic Webcast. And then we'll show how to get an event, how to read error code if you do something incorrectly. So there's a limited amount of data you can have in one advertising packet, and we can try to change the device name. Now we change this to a very long name, and we compile again. We go into debug mode. add a breakpoint here to see what error code is when we are running this program. So here you can see it's 000, which is good. It's error of success. But if we set a breakpoint down here when we are actually setting all the data, and we run the restart program, you can see that it's not 0, it's C. Then we can go to the function definition here by go to reference, and we can see that we have this, if it returns NRF error data size, not all the requested data could be put into the advertising packet. Then we can go to the definition of this, and we can see that it's 12, which is C. So now let's try to get an event from the SoftDevice. We need to change the name back so it's accepted. So when we have set this up, so we have this BLE event dispatch here, where the events will be set, where will be sent when there are any events. This is defined here. Here we have another function on BLE event, and here we have a switch statement which checks the event ID in the header, and here then we can see what the event that is has come from the SoftDevice. So then we need to go out of debug mode to compile with a short name, and we go into debug mode again. So here we now set a breakpoint at the BLE gap event connected event. So we can try and open master control panel again and connect to this and see if we actually get the event. So we select our device, and then we can connect. Okay, so we see we get the event, so the event handling is actually working. Yeah, and because we have a breakpoint here, we receive the link loss. So yeah.
Okay, so we finished with the first webcast, and we have been collecting your questions during the sessions, and now we will try to answer those. You still can type your questions. We will try to answer as much as possible, but if we cannot answer all of them, please create your own question on DevZone and we'll try to answer you there. Okay, let's start.